So how does the change in volume affect an equilibrium? Well, let's back up here because it's been a while. So we had talked about the change in concentration, how that affected an equilibrium. And we said if you increase the concentration of a reactant, an equilibrium will fight back against any change that you make to it. It's a little bit like me. I do not like change unless it's my idea, right? So if you impose change on me, I'm going to resist you, which drives my husband bananas. Poor man. But if you increase the concentration of the reactants, the reaction will shift in a way to reduce that concentration. So it'll try to counteract what you did to it. So let's talk about how volume change can affect the equilibrium. So here we're talking about gases. And so we have to call upon our knowledge of gases. What happens when we decrease the volume of a gas? What happens to the pressure? It goes up, right? And if we decrease the volume, that's what I was saying. If we increase the volume, if we make the container bigger, the pressure goes down. Because we think about those gas particles. Okay, the pressure arises from the gas particles hitting the walls. If we make the container smaller and crowd the particles closer together, they're going to hit the wall more often and increase the pressure. If we make the container larger, they have more space and they're going to run into the walls less often. And so the pressure will decrease. Changing the number of moles of gas also affects the pressure. If you take a fixed volume container and you put more gas into it, the pressure goes up because there's more particles. So we have to keep these ideas in mind. Question?
Do all gas particles move at the same, the temperature, like let's say at room temperature, how fast do they actually move?
Well, the temperature, the question is how fast do gas particles move and do they all move at the same speed? Gas particles move at different speeds. Okay, so we've got fast ones and slow ones. The average speed is related to the temperature. So if you increase the temperature, the average velocity, the average kinetic energy will increase. But you'll still have some slow ones and some fast ones. So you have this wide distribution of velocities. It's kind of like people, you know. We're not all the same. We're different, but there's averages.
But they all fill up 22.4. Like, how can they have different speeds and all fill up the same volume?
Okay, so in 1 mole of gas at STP, it will occupy 22.4 liters.
Mm-hmm.
Okay, in that volume, that 1 mole of particles, some of those particles are moving faster than others, and some are moving slower. But the average kinetic energy of that gas will be the same as the average kinetic energy of another gas under the same conditions.
Like the bigger ones go slower, right?
Well, yeah, if you're comparing like nitrogen and helium, nitrogen is a much larger gas particle. So its velocity is going to be less because its mass is higher.
That makes sense.
Okay, but even within a sample of nitrogen gas where all the particles have the same mass, some of them are going faster and some are going slower. But the average is what's measured by the temperature. Good questions. So, in talking about gas laws in Chapter 11, we did not talk about the gas itself changing its number of moles. We talked about us adding or taking gas out. But if we're talking about a chemical equilibrium, the equilibrium can shift to change the number of gas particles, and it'll do that to relieve pressure. So let's look at this example. So here we have nitrogen gas reacting with hydrogen gas to form ammonia. This is a reversible reaction, and so in this container we have established equilibrium. So it's reacting in the forward direction and in the reverse direction at the same rate. On the reactant side, we have a total of 4 moles of gas particles. Remember that mole is a counting number. So in the picture, we're showing 4 molecules, but we can multiply that up, and this represents 4 moles of gases. In the products, because of how they combine, there's only 2 moles of gas. So when the nitrogen and hydrogen combine together, the number of particles decreases. So what happens if we take this container and we push down on it and decrease the volume? What happens to the pressure inside? The pressure goes up. Okay? This is an equilibrium reaction. It's going to fight back. You increased my pressure. I'm going to do whatever I can to reduce that pressure. So this side has 2 particles, and this side has 4. If the equilibrium shifts to the right, there will be fewer particles. Fewer particles will reduce the pressure. Does that make sense? The only way to remember this stuff is for it to make sense. The way I remember and would figure out problems is I would actually just reason it out, because otherwise it's just seemingly random things. So you decrease the volume, that increases the pressure. The reaction's going to shift to counteract that. So it's going to try to undo what you did to it. So it can't do anything about the volume, but it can shift back one way or the other to make fewer particles. So it'll shift this way to have fewer particles.
So if it was a chemical reaction with the same amount of molecules on each side, then it wouldn't be affected by pressure?
Exactly. Yeah. If you have the same number of particles on each side, then changing the volume, changing the pressure doesn't do anything to the equilibrium. Here's an illustration of increasing the volume. So we pull up on the piston, we increase the volume. That causes the pressure to drop. The reaction's like, I don't like that. I liked where I was. I want to make it bigger. I want to increase the pressure. And so then it's going to shift the other way to make more particles. Because the weird thing about gases is it doesn't matter what the particles are, it's the number of particles that matter. It's very, very different than liquids and solids, very different. Which is one reason that gases, in some ways, are much easier to work with, because they're simpler in that way. So increasing the volume will cause this to shift to the side with more particles to counteract that decrease in pressure. So here's the summary. Decreasing the volume will cause the reaction to shift to the side that has fewer moles of gas particles. Increasing will cause it to shift to the side with more. And if the moles of gas particles on both sides of the chemical equation are equal, then changing the volume or changing the pressure will have no effect on the gas. So here's an example. So consider this reaction, chemical equilibrium. We've got, everything's in the gas state here. So we've got SO2 and O2 and SO3. And they're asking us, what's the effect of decreasing the volume? Well, let's look at this. On the left side, I have 2 particles here and 1 particle there. You can think of them in terms of individual molecules or moles. So 2 moles and 1 mole. So on the left side, I have a total of 3 moles of gas particles. And on the right side, I have 2. So you have to look and see which side has more particles. So if I decrease the volume, so I'm going to push down, make the volume smaller, what does that do to the pressure? Makes it go up. So this system, this reaction is going to shift to make the pressure go down. To have the pressure go down, you need fewer particles. So it will shift to the right. Does that make sense? So what's the effect of increasing the volume? Will be the opposite, right? But let's reason it out. Increasing the volume decreases the pressure. The reaction wants to move in a way to restore the pressure. So you decrease the pressure, I want to increase the pressure, so it's going to go to the side with more particles. So it will go to the left. So those are the sorts of questions you should be able to answer.
What about for reactions that aren't reversible, or is this only talking about those specific?
This is only for reactions that are reversible.
Okay.
This is only for things at equilibrium. If a reaction is not reversible, then there's no equilibrium. Because equilibrium requires that there be forward and reverse reaction.
Even if the reaction was not reversible, if it was under pressure and there was less molecules on the other side, it would still speed up that reaction, wouldn't it?
This is not talking about speeding up a reaction.
Well, it wouldn't?
No,
Just shifting the equilibrium?
it's just shifting in equilibrium. And we'll talk about things related to that in a section that's coming up. It has to do with activation energies and catalysts and things like that. So what this does is, another way to think about this, so we have a forward reaction. And we said that the forward reaction was dependent on the concentration of the reactants. More concentration, you have more collisions, more opportunity for reaction. And then the reverse reaction is, the rate of that is dependent on this concentration. Well, when you squish a gas, what do you do to the concentrations? You increase them, right? And so we're actually increasing the rates of both, in both directions. We are increasing the rates. But it will shift to compensate for that pressure change.